Okay, today we're going to have a look at applications of de Moivre's theorem. So, de Moivre's theorem, as we've said, allows us to quickly raise a complex number to higher powers without having to need things such as the binomial theorem to expand the complex number. So, one of the most useful applications of de Moivre's theorem is allowing us to prove complex identities in trig. So, for example, if we want to expand part 1, cos I sine all to the power of 3, using de Moivre's theorem, we know it's just going to be cos 3 theta plus I sine 3 theta. However, if we were to use the binomial theorem or Pascal's triangle, we know it would be 3 choose 1 times cos cubed theta, 3 choose 0, plus 3 choose 1, which is 3, times cos squared theta, I sine theta, plus 3 choose 2, which is 3, cos theta, I sine theta squared, plus I sine theta cubed, 3 choose 3 is 1. And if we have a go at simplifying this, we've got cos cubed theta plus, I like to write all of the real things first and all of the imaginary things second. So cos cubed theta, now I squared is minus 1, so this is going to be minus 3 cos theta sine theta, and then we've got our imaginary things last. So we've got 3 cos theta I sine theta, and then I cubed we looked at in an earlier video is minus I, so minus I sine cubed theta. Now part B says hence show that these following things are true. Now we learnt in a previous video that we can equate the real and imaginary components of an expression. So we've said that part 1 and part 2, well, they're the same thing because it's two different ways that we can expand cos plus I sine cubed. So that means cos 3 theta, which is the real component of that expansion from de Moivre's theorem, is simply these things here, which is cos cubed theta minus 3 cos squared theta sine theta. And the question says prove it's 4 cos cubed theta minus 3 cos theta. So it's indicating to us that we would like to get rid of the sine. Now I've realised potentially here, I put the squared in the wrong spot, I'm sorry. So that squared should go there. If we have a look, the squared is up here on the sine, so that means the squared's there. And then what we can do is we can replace the 3 cos theta sine squared theta, where we can make this 1 minus cos squared theta, and we get cos cubed theta minus, if we expand that, 3 cos theta plus 3 cos cubed theta. And of course that's going to give us 4 cos cubed theta minus 3 cos theta. And that's that part done, QED. Have I left room here? No, I'm going to have to add another page. Right. Part 2 of that wants us to deduce things about sine of 3 theta. We know that sine of 3 theta is just equal to the imaginary component of our expansion, because we know that if we have an expansion, we can equate the real and imaginary components on the right and left hand side. Now we've agreed that the imaginary components of this expansion are equal to 3 cos theta. We don't need to write the I because we already are saying that these are the imaginary components, so we don't need to do our job twice. And again, I made the same mistake. There's a squared there because there's a squared there. So there's a squared on that cos. And then what we can do is replace the cos squared with 1 minus sine squared theta minus sine cubed theta. And we've got 3 sine theta minus 3 sine cubed theta minus sine cubed theta, which of course is going to be 3 sine theta minus 3 minus 1, or minus 3 minus 1 is minus 4 sine cubed theta. And that's that done. And then part 3, we've got to prove that tan 3 theta is that. Now we should know by the time we're in extension 2 that tan of theta, and same as tan of 3 theta, is sine over cos. So sine 3 theta over cos 3 theta. But we have expressions for sine 3 theta and cos 3 theta now. So sine 3 sine theta minus 4 sine cubed theta all over 4 cos cubed theta minus 3 cos theta. And we have to prove that it's equal to tan of theta minus tan cubed theta over 1 minus tan squared theta. Now, there's a number of different ways that we can go about doing this. A smart way could be looking at what we want on the bottom, and by dividing everything by the same expression. So on the bottom we want 1 minus 3 tan squared theta. So we want to see, is there anything I can divide by to get that? Now I'm noticing we've got 3 tan squared theta, and down here we've got 3 cos theta. So we'll see what we can divide this by. Potentially what I'm looking at doing is replacing and factorising a sine theta out from the top. We've got 3 minus 4, 1 minus cos squared theta. And on the bottom we can take out a cos theta. We've got 4 cos squared theta minus 3. And we simplify that, we're going to get sine theta, 4 cos squared theta minus 1, all over the same thing, cos theta, 4 cos squared theta minus 3. Now, we know that sine or cos of theta, we're trying to get tans involved here. So we know cos of theta is sine of theta over tan of theta. So we can say this is sine of theta over 4 sine squared theta over tan squared theta minus 1, all over cos theta, 4 sine squared theta over tan squared theta minus 3. And then we can just do some cleaning up. This is going to be sine of theta outside of 4 sine squared theta minus tan squared theta all over cos theta, 4 sine squared theta minus 3 tan squared theta. And the denominators of tan squared of theta, this one and this one, both will cancel because we can cancel denominators that are both common on the top and the bottom of a fraction. Okay. What we can do next is use some identities. So we've got sines and tans, and we don't want any sines or coses. We want exclusively tans. Now we know that sine theta over cos theta is tan theta, which means sine theta is tan theta cos theta. So we can say this is sine theta 4 cos squared theta tan squared theta minus tan squared theta all over cos theta 4 cos squared theta tan squared theta minus 3 tan squared theta. And then if we take out a tan squared theta, we've got sine theta tan squared theta over 4 cos squared theta minus 1 over cos theta tan squared theta, 4 cos squared theta minus 3. Now we're getting somewhere because I can cancel the tan squared and I can cancel the sine and cos potentially to become tan. I might just straight up cancel these tans, and I might use another identity, and it's the fact that sec is 1 on cos. So sine theta outside of 4 on sec squared theta minus 1 over cos theta 4 on, and that should be a sec, I'm sorry, sec squared theta minus 3. And that actually gets us sine theta 4 minus sec squared theta over cos theta 4 minus 3 sec squared theta. But we know sec squared theta is 1 plus tan squared theta. So this is sine theta 4 minus 1 plus tan squared theta over cos theta 4 minus 3 1 plus tan squared theta and that's going to give us sine theta. Here we've got 4 minus 1 and then minus tan squared theta. 4 minus 1 is 3 minus tan squared theta over, on the bottom, we've got 4 minus 3 is 1 minus 3 tan squared theta. What we can also do as a final step is sine over cos becomes tan. And that's actually what we wanted. We wanted tan theta minus tan cubed theta, or 3 tan theta minus tan cubed theta over 1 minus 3 tan squared theta. Now there is a simpler way of getting there that I'm going to show you in class, but I wanted, for the purpose of this, to practice some of this complex manipulation of sine and cos, which is very, very important for proofs. Okay, part C. Solve x cubed plus 3x squared minus 3x minus 1 equals 0 using the substitution x equals tan theta. So what that gives us is tan cubed theta plus 3 tan squared theta minus 3 tan theta minus 1 equals 0. However, what we can do is we can plus some things onto the other side. So we can say this is 3 tan theta minus tan cubed theta by plussing this and this to the other side. And that's going to leave us with 3 tan squared theta minus 1, right? We've got 3 tan theta minus tan cubed theta which is equal to 3 tan squared theta minus 1. Now what we can do is we can divide some things onto the other side. I just might check that we haven't made any mistakes. So far, we've got x cubed plus 3x squared minus 3x plus 1. So we've gone tan cubed theta plus 3 tan squared theta minus 3 tan theta minus 1. We have minused the tan cubed theta to the other side and plussed the 3 tan theta to the other side. That's fine. And we've left the other things there. Now what we can do is we can divide some things down to the bottom. So 3 tan theta minus tan cubed theta all over 3 tan squared theta minus 1. And that equals 1. Now what we can do is we can go, okay, this is almost what we got in part 1. But if I multiplied the bottom by -1, then we would actually get what we want. So 3 tan theta minus 10 cubed theta. If we multiply the bottom by -1, we're going to get 1 minus 3 tan squared theta. And that gives us over here -1. All right. But we've proven earlier that this is equal to tan of 3 theta, and that equals -1. So we're going to solve the equation tan of 3 theta equals -1. So tan inverse of 1 is pi on 4. So tan inverse of -1 is going to be 3 pi on 4, or 7 pi on 4. And we can keep going. We can be plussing 2 pi to both answers. So 3 on 4 plus 2 is, as a fraction, 11 pi on 4. And 7 on 4 plus 2 is 15 pi on 4. And then we'll do it one more time. 11 on 4 plus 2 pi is 19 pi on 4. And 15 on 4 plus 2 pi is 23 pi on 4. So you would have learned how to do that in advanced maths. Then we can go divide everything by 3. So we get pi on 4, 7 pi on 12, 11 pi on 12, 15 pi on 12, 19 pi on 12, and 23 pi on 12. Now, what we're trying to do, if we go up to here, is we're trying to actually get for, even though we've technically finished part C, we're trying to get for expressions for pi on 12 and 5 pi on 12. So if we just quickly finish off part C, we know that x was tan theta. So x equals tan theta. So x equals tan of pi on 4, tan of 7 pi on 12, and so on. All of those options. And the next part wants us to prove that tan of pi on 12 times tan of 5 pi on 12 is equal to 1. Now, whenever you see questions like this, you always are thinking the sum and the product of the roots. But the problem with all of our roots here is that none of them are pi on 12 or 5 pi on 12. So we actually have to investigate these roots here and see if any of them are the same as pi on 12 and 5 pi on 12, or at least similar. So if we get pi on 4 and we minus 2 pi, we get minus 7 pi on 4. If we get 7 on 12 and we minus 2 pi, we get minus 17 pi on 12. If we get 11 on 12 and minus 2 pi, we get 13 pi on 12. So potentially, it's none of these solutions. We might have to keep investigating. So the one that's going to be pi on 12, if we have a look, we've got 3 pi on 4, 7 pi on 4, 11 pi on 4, 15 pi on 4, 19 pi on 4, and 23 pi on 4. And we have to, again, look at these and see which one is the same. Now, we've discussed that 7 pi on 4 is not quite the same. So what we might actually have to do, we've got now 19 on 12, we'll check 19 on 12, 19 pi on 12 minus 2, we get 5 pi on 12, we get 23 pi on 12 minus 2. That actually does work. This one, 23 pi on 12, is the same as minus pi on 12. That one's good. And we'll see if any of these ones are 5 pi on 12. This one here is 5 pi on, or minus 5 pi on 12. That's good. We have to investigate our solutions and see which one are actually the same. So we know actually, if we kept continuing this sequence, that tan of 19 pi on 12 is solution, as is tan of 23 pi on 12. But we've discussed that 19 pi on 12 is the same as tan as minus 5 pi on 12. And this one is the same as tan of minus pi on 12. We know that we can minus 2 pi's, you would have seen this in advanced maths, minus 2 pi from our solutions multiples of time, and we still get expressions that are the same answer. You can plus 2 pi to an angle and it means the same thing as well. Now, since the equation that we solved was a cubic equation, it means that there's only 3 answers. But we have figured out there's actually 1, 2, 3, 4, 5, 6. So what we can do is, since there's only allowed to be 3 answers, we can select any of these solutions to be our answers. So we know that tan of pi on 4 is equal to 1, and we're going to select one of those because I've only got 2 tans here, so it's implying the third one is 1. And if we go up to our equation and consider the product of the roots, we've got minus, plus, minus. The product of the roots is 1. So we know that tan of minus 5 pi on 12, which is one of the 6 roots we've selected to be our solution, times tan of minus pi on 12, times 1 is equal to 1. Right? So we've figured out that there actually are 6 solutions to this equation, but since it's a cubic equation, we're only allowed to have 3. So we can pick any of these 6, any 3 of those 6, and they're going to be valid solutions. Now, minus 5 pi on 12 and pi on 12 are angles that are in the 4th quadrant. And an expression that we know for tan is that tan of minus theta is the same as minus tan of theta. So this is the same as tan of 5 pi on 12, but with a minus out the front. And this is the same as minus tan of pi on 12. And we've got times by 1. Those 2 negatives there make a positive, and we get what we wanted. Tan of 5 pi on 12 times tan of pi on 12 equals 1. And that's done. Thanks for watching.